Very often the power applications are driven by the AC mains. Here in Europe, the AC mains are 230 volts RMS and are operating at a frequency of 50 hertz, as you can see on this slide here. In other parts of the world, for example in US, the AC main is only 110 volts and operating at 60 hertz. The frequency isn't that necessary a game changer for power electronic circuits, but the voltage certainly is, as there is actually a factor of approximately 2 between those. On the other end, the application very often requires a lower voltage than the AC mains than the grid actually provides. So very often in very simple solutions, and that's the first ones we're going to focus at, very simple solutions, the first stage you would see in a power electronic circuit is a transformer, a 50 hertz, 60 hertz transformer to actually transform the voltage down here. So the output voltage of the transformer here is lower and closer to the application than what the AC mains actually provide. Now after that transformer, typically the next thing you would see is a kind of a rectifier here. The most simple kind of rectifier you can imagine is a half-wave rectifier. In a half-wave rectifier, you only got one diode up here, and then at the output you have a capacitor to store the energy and provide energy to the load when the grid voltage is too low. That looks like that. If the grid voltage is a sinusoidal voltage, good approximation for what it really is, but both in the US and in Europe and in all places of the world, it's supposed to be a sinusoid waveform. So if the grid voltage looks like that, sinusoidal waveform here, then the diode is conducting whenever the grid voltage is higher than the actual existing voltage in the capacitor at that same very moment. And if the grid voltage is lower, so if we're getting closer to the zero voltage crossing here of the sine wave here, then the capacitor would supply the load with the energy it needs. That gives us a capacitor voltage that looks approximately like that. It's getting charged whenever the grid voltage is higher, and whenever the grid voltage is too low, it would get discharged over and provide energy to the load. So the only time when it's actually getting charged is also the only time when we actually have an input current, and that's during this period shown here. Otherwise, the current through that diode here is 0. Another rectifier is the full bridge rectifier, even more commonly used than the very simple half-wave rectifier. I guess that's the most commonly used rectifier for those kind of 50-60 hertz applications. But as we later will see, we can also use these kind of rectifiers actually operating at higher frequencies. But for now, let's have a look when they're directly applied to the AC mains as they are in this case here. So Vin is again the AC mains over here. When the AC mains are positive and when the absolute value of the AC mains of the input voltage here is higher than the capacitor voltage, the voltage across the capacitor over here, then we are charging the capacitor through those two diodes, the upper left one and the lower right one here. Now when the voltage is lower, but still the amplitude is higher than the absolute value of the capacitor voltage, we're using the upper right-hand side diode and the lower left-hand side diode, and the AC mains are charging it from here. Now this terminal here is the more positive electrical potential here, and that terminal here is the more negative one here. So we are actually charging this way over here, going through the upper right diode, through the capacitor, and back to the source through the lower left-hand side diode here. Still charging the capacitor. In between, we would typically see some stages where the AC mains are crossing the zero voltage again, or too low to actually forward bias any of those diodes here compared to the current capacitor voltage. And in those periods the capacitor would hold up the voltage and the energy supply to the RL, where RL, the L stands for load, to the load resistor here. Many applications can very simply be modeled as just being a resistor. For the sake of this course here, most of it is going to be handled as a resistor. In reality, it might be more tricky. The loads are more spiky and can have other characteristics. Now, as we have the two different voltages to deal with, and most often you would want to sell the product globally, then you're speaking about a universal AC mains power supply. You would need to deal with the two different voltages, the voltage amplitudes that the grids on the planet here are providing. See, on the one hand, you got the lower voltage, the 110 volts, and on the other hand, you got the higher European mains voltage with the 230 volts. And one way to do that is actually using the kind of same thing again as we've just seen with the full bridge rectifier, but splitting this capacitor over here in two capacitors, C1 and C2, and then adding an extra switch in here. In this case here, the switch is closed, so the switch could also be open, then it would look like that. If that switch is open, the operation is basically the same as we've just seen from the full bridge rectifier, and you would rectify the outputs to the peak voltage of the AC mains minus whatever the capacitor discharges the cap. But for now, let's keep it closed. So this one is a steady connection. Then we have a different circuit here. And what happens here is when the grid voltage is positive again, and again, it's got to be high enough to actually charge the capacitance. It's got to be high enough to forward bias this diode here. You would only charge the upper capacitor. So that's a half-wave rectifier, as we've seen previously, but still rectifying to the peak of the AC mains. So now if the AC mains are 110 volt, the peak would be around 155 volts in this case here. So that's what we're doing with the positive half wave of the grid. And with the negative half wave, we would only forward bias the lower left side diode here and only charge the lower capacitor here. Note that the upper one is still charged from the positive cycle of the mains, so we still get around 150 volts, 155 volts on the upper capacitor. And then we are doing the same thing with the lower one, so we are adding actually 2 times the 150 volts in the US example. So the US example would be 110 volts here at the input, and that's RMS. So we would charge the upper capacitor here to 155 volts. And so we would do with the lower one. That means the total voltage across the resistor here would be 2 times the 155, and that's 310 volts. If we open that switch here, then we get the European mains voltage, and the European mains voltage is closer to that same voltage again. So everything downstream here would need to operate at the same voltage in Europe as it would be operating in US. In Europe, it would have 325 volts at the output here, if that switch would be opened over here. And then we still got the operation when the grid voltage is too low to actually charge any of the caps. None of the half-bridge rectifiers is actually conducting. The diodes are kind of turned off. Then again, the two capacitors here would supply the energy to the load.